Hello there. Welcome back. This is the last section of thermodynamics. I know you're just going to cry. So this is the fourth installment of this particular subject. And so I wanted to just tell you a little bit about what we're going to do in this last one. This is kind of like the exciting climax. We're going to calculate something called Gibbs free energy by using values of enthalpy and entropy, and also by using standard molar free energies of formation from the table that we all know and love, Appendix K. And then when you should use each type of calculation. We're going to use delta G to predict whether a process is going to be spontaneous or not at constant temperature and pressure. And we're going to understand how changes in temperature can affect how spontaneous the process is. And then finally, we're going to predict temperature ranges for spontaneity of a chemical or physical process. So we've had delta H, which is change in enthalpy. We've had delta S, which is change in entropy. And now we've got delta G, which is the Gibbs free energy. And this is a measure of maximum useful energy. That is the energy that can do work from a process at constant P and T. Because remember, we've got heat loss a lot of times, which is waste or whatever. So that useful energy that we really have available that we can perform a process, that's what Gibbs free energy gives us. And so it also gives us a measure of, is it going to be spontaneous or not? The Gibbs overall is going to tell us it is, it isn't, or it's at equilibrium. That is, it's going to kind of go back and forth. So the sign conventions for the delta G, if delta G is greater than 0, that is, it's our positive number, it's non-spontaneous. So positive is non-spontaneous. If it's a negative number, then it is spontaneous. Okay, so it is spontaneous. So you need a negative delta G to show it being spontaneous. If delta G actually equals 0, then it means that the forward and the reverse reactions are occurring at the same time, or they have the same probability of occurring, so that will be at equilibrium. So when we solve for delta G, it's going to be very, very similar to what we've done already. The delta G is going to be, can you guess? Delta G0 at 298 is going to be what? The sum of all the N delta G0 of the products minus the sum of all the delta G0 of the reactants. Now, by now you should be getting pretty good at this, right? So the delta GF is that delta G of formation. We're going to get that number from Appendix K, okay, and it's there for all of our compounds that we've been looking so far, and it'll be there for these. N is notice I've got an N here, okay, N. Okay, N is the number of moles of reactant or product from the balanced equation, right? Okay, or delta G0 is equal to enthalpy minus T delta S, or delta G is equal to delta H minus T delta S. You can get all of these numbers from where? Yep, you got it. If they're the 0 values, these all come from Appendix K. If they're these values, that means they're not at standard temperature and pressure. Okay, and so you might have to do some crazy stuff. Maybe not. Okay. All right. So if we're going to calculate delta G for a reaction, let me see if I might give you the reaction. Yeah, that'd be nice of me, right? Okay, so we're going to use our old buddy propane and combust him to form carbon dioxide and water, and we know that's probably going to be what? Exothermic, right? Because we're burning stuff. Now, the delta G of the reaction, we know we're going to have to go to Appendix K, and we're going to have to look all these things up. We know that we're not going to have to worry about the element water because it's not going to have anything. It's going to be a 0, right? So we've got 3 things to look up the values of. And so when we look up, we've got CO2, and remember these are from Appendix K values, and these are the delta G zeros, okay? And they're going to be in kilojoules per mole. And a lot of these are different, so make sure that you're really paying good attention to that. Okay, so the CO2 is going to be negative 394.4, and water is going to be a minus 237.3. This is delta G, so the number is going to be a little bit different. And then the C3H8, the propane, is going to be a negative 23.49. Make sure you look those up. Sometimes I make mistakes. I know, it's hard to believe. Okay, so your delta G0 at 298 is going to be equal to your products minus your reactants. Like I said, we should be getting good at this. It just asks what, if it wants delta G, if it wants delta H, or whatever. If you're doing it by the tables, you should be able to do this pretty easily. Okay, so our products is going to be, we've got a 3 here. This is a balanced equation. So 3 times a negative 394.4 plus 4 times our water, which is a minus 237.3. And then we're going to say minus 1 times a negative 23.49. Okay, and then it was 5 times 0. So we don't have to worry about that one, right? Okay, and that's all going to be in kilojoules per mole. All right, and so when we do the math, you should get, and so this is going to be a negative, and then it's going to be plus what this 23.49, right? And then the 0 was out. So do this calculation right here, get your number, add that to 23.49, and we should get a negative 2108.9 kilojoules per mole. All right, so see if that's what you got. Okay. Whose law was this? Thank you, Mr. Hess. You make it so easy for us because as long as there's something in that table, we got it, right? So you can do delta H's, delta S's, delta G's. That's the easy part. Interpreting this stuff is where it gets a little tricky. Okay, so we know that the free energy has the relationship that delta G, the Gibbs free energy, is equal to delta H minus T times delta S. So if we look at the delta H and T delta S, we can determine the effect on the delta G sign. So we can actually tell if, by just looking, if we know those numbers without doing a calculation, we can tell if it's going to be spontaneous or not. So if we have a negative delta H and a positive delta S and a negative delta G. Now, delta G is probably going to be negative. It's probably going to be whatever the delta H is. Why? Because the delta H is big. And the entropy number, if you remember, was like decimal places. So it's small. Okay? So the delta H is negative. The delta S is positive, so the delta G is negative. It's not always true. That's why we have to know what it is. That is going to be spontaneous at all temperatures. Okay? So if you have minus plus minus, it's spontaneous no matter what the temperature is. If it's a negative delta H, but it's a negative delta S, it's the delta G sign is going to depend on the temperature. And so it will be spontaneous only at low temperatures. If the delta H is positive and the delta S is positive, it's also temperature dependent for G. So it will be spontaneous at high temperatures. I know you're good at patterns by now, so you know this next one. If it's a positive delta H and a negative delta S, the delta G will be positive, and it will be non-spontaneous at all temperatures. Okay, so negative, positive will give us a negative. That will be spontaneous no matter what. Positive delta H and a negative delta S is going to give us a positive delta G. That will be non-spontaneous at all temperatures. Where you got to do some interpretation, if you've got negative, negative, that's only going to be spontaneous at low. If you've got positive, positive, only at high, because your delta G will be dependent on temperature. So how I try to kind of remember this relationship is that we know delta H tends to be a forward reaction. So if you've got a negative delta H with the positive S, then your delta G will be the same as your delta H spontaneous no matter what. If your delta H is positive starting off, then it's going to be non-spontaneous, so it'll be plus minus plus. Low is negative, okay, so it's spontaneous at low temperatures. High is positive, so plus numbers, so it'll be spontaneous at high. Okay, this is something you need to know because you'll be asked questions about this, and so you'll need to be able to interpret that. So finding temperature at equilibrium is kind of easy because at equilibrium, if you remember, delta G is equal to 0. And so what you can do is you can say, okay, for an equilibrium reaction, temperature is equal to delta H divided by the delta S. So whatever you have calculated those to be. Just make sure they're in the same units, because a lot of times, since delta S is small, you're going to see it in joules per mole instead of kilojoules. So make sure you get kilojoules and joules so that they line up. And determine if it's spontaneous at another temperature, because it's just going to depend on what? It's going to depend on your negative and your positive, right? From that thing we just looked at, right? Go back and look at the table. Okay, you're good. All right. Okay. Now, we have talked about several formulas for this. We've said, all right, at equilibrium, okay, G equals 0. So that allows us to say that T equals delta H over delta S. That's just a rearrangement from one we had earlier, okay? If it's not at equilibrium, all right, then we have to have delta G in there. And so if it's not at equilibrium, then we're going to have delta H, and we're going to do the standard ones, minus delta G, okay, divided by T will give us delta S 0. And you can use this, rearrange it however you need to solve for different things. Okay, if you're looking for delta G or delta H or whatever, you can just rearrange it. Okay. This particular problem, we're looking for delta S 0. So that's why I rearranged it to have the delta S 0. Okay, so calculate delta S 0 at 298 for the following reaction. The delta H 0 is a negative 2219.9, and the delta G is a negative 2108.5. What is the delta S? You just plug it in, okay? What did we tell you? They're both at what? 298. So that's your temperature, okay? It's constant, all right? So all we do is plug in. We're going to use delta H 0 minus delta G 0 divided by T equals delta S 0. So our delta H is negative 2219.9 kilojoules minus delta G, which is a minus 2108.5 kilojoules, divided by the temperature, and the temperature is in Kelvin. All right, and so negative 2219.9 plus 2108.5 is going to give us, let's see, a 2108 is going to give us a negative 0.374, unless I messed that up. Okay? So that is our delta S. Now, spontaneous or not, we have a negative delta H, a negative delta S, and a negative delta G. So let's go back and look for a minute. We have negative, negative. When we have a negative, negative, that means it's only going to be spontaneous at low temperatures. Okay? Is 25 degrees C a low temperature? No. So it will not be spontaneous. See how that works? If it was like below freezing, yeah, probably would be. Okay? All right. Okay. Now, here's just an interesting way to do this. We can actually estimate the boiling point of water, the normal boiling point of water, with thermodynamic data, okay? Because we know that water going from a liquid to a gas is going to be in equilibrium, right? Because water is with itself. Okay, and because it's in equilibrium, whenever it is, we know that delta G is equal to 0. So that allows us to say that T is equal to delta H divided by delta S. So what do we need to do? Well, we need to first figure out what delta H is for this, or delta H0 for this reaction. All right, because what I'm going to do is I'm going to assume that it's going to, if normal boiling point of water is about room temperature, so that's 25 degrees C, right? So that's 298, and that's what all my numbers are set up for. So I can go to my table with my delta H0, my delta S0, and it will allow me to calculate this. So my delta H0 is going to be equal to the delta H0 of the gas, because that's the product, right? H2O in equilibrium with the gas, because I'm boiling it and I'm making it a gas, okay? So the gas minus the delta H0 of the liquid of the water. So when I look up in Appendix K, H2O liquid is minus 285.8. And for the gas, it's going to be minus 241.8. Okay? I think I got those the right way. Got to look really hard, because sometimes, especially when they're the same thing. All right, so that would mean that you have a minus 241.8 minus a negative 285.8. Okay, so when I do those, I'm going to get a positive 44 kilojoules, because those were all kilojoules. Okay, so I've got a positive 44 kilojoules for my delta H. So already that kind of tells me I had to put heat into that to make water go from liquid to gas. Does that make sense? Yep, I think I have to do that. All right, second step, I need the delta S. The delta S0, because I'm assuming we're at the 25 degrees, is going to be the delta S0 of the gas minus the delta S0 of the liquid water we're talking about here. So again, the S numbers, those are the delta H numbers. The delta S numbers from Appendix K are going to be 69.91 and 69.91 for the gas, and the liquid is going to be, no, I got them backwards. That's the liquid. I keep looking away. And the gas is 188.7. Okay, so I go back and I plug those in. 188.7 minus, remember these are always positive numbers, 69.91. All right, and that's going to equal 118.8 joules, right? Because this is in joules. This one was in kilojoules. All right, so I need to convert that to 1188 kilojoules. So they'll be in the same units. Otherwise, I'll get all messed up. Okay, so I now know my delta H and I know my delta S. And so my original, I know that T is equal to, if it's at room temperature and it's at equilibrium, okay, it's going to be delta H0 divided by delta S0. So I plug my numbers in and I've got plus 44 kilojoules divided by 0.1188 kilojoules, and T is going to equal 370, which is K, minus 273K will give me 97 degrees C. Cool, huh? All right, and so that I could actually calculate the normal boiling point of water by using the table numbers. All right, guess what? We are done with thermodynamics. I know I'm very sad, and I know you are too. One last thing I do want to show you how to calculate, though, because we'll use this in the labs. Percent error. In percent error, we use this a lot because this is basically how far off we were with the actual measurement. We got our answer was 370 Kelvin, right? Okay, so 370 Kelvin is what we got. So our value was 370 Kelvin. Well, we know that the actual boiling point of water is what? 100. Okay, so 100 would be, so the true value is 100 C plus 273 would actually be 373 Kelvin. All right, so how close were we to that true value? Okay, well, we can set that up by saying what we found. Okay, so the actual value we found, which was 370, minus the true value, which was 373, divided by what the true value should have been, okay, times 100. And that's going to give us percent error. All right, and when we do that, we're actually going to get 0.80%. That is a percent error of less than 1%. And that's really good, in case you're wondering. Okay, so store that back because we're going to be using percent error. The actual or experimental, sometimes you see it called actual or experimental value, minus the true, and then divided by the true, times 100. And that'll give you your percent error, how far you were from the true value. And that's really